we will deal with what is called the Debye model. Okay. So, this Debye model is an approximation but it is something which is reasonable, because so I mean look at the various features of it. What is the frequency term is appearing here in the denominator, right. So, at 0 frequency, what is the term that survives in this expression? Epsilon s, right. So, this is, you can call this the static value. Okay. Then what happens when at extremely large frequencies? Right, you just get epsilon infinity. So, that is the high frequency case, very high frequency case, right. And this tau over here is what is called the relaxation time. Okay. So, this is perhaps one of the simplest models for frequency dependence of permittivity, right. So, in our previous expression over here, we did not say anything about what is the form of epsilon r as a function of omega, right. So, we are going to start with this as one form and see, do I still have to store all the past history, or is there some clever thing I can do? Okay. So, that is sort of the objective of what we are trying to achieve. Okay. So, this whole term over here, it will appear many times. So, I am going to give it a shorthand notation. I am going to call it beta. Okay. Since it is in the frequency domain, I am putting a tilde on it. So, this is beta tilde of omega. Okay. Again, looking back at the time domain picture, if I wanted to implement that model, what do I need? So, these guys, electric fields, they are coming from the calculation, from the E cell. So, they are not functions, they are just numbers. What is left is this guy. So, this is in which domain? Frequency or time? It's time domain, right. So, I started with some frequency domain version of the permittivity, which is the dispersive nature. Now, in order to implement this D, because I will need this D to put it into the update equations, right. What are the update equations? So, D dot is equal to curl of H, supposing I say this. So, I need D in the time domain, then I need to take its derivative. So, to get D in the time domain, I need this epsilon r in time domain. But what I have started with is, starting point is frequency domain, that is the simplest place to start with. So, I need to take now the inverse Fourier transform of this expression in order to get epsilon r as a function of time, so that I can plug it back in. Starting, it is just put omega equal to 0. What will happen to epsilon r? You will get Es, or sorry, epsilon s. So, it is called static, because 0 frequency. Alright. So, if I want to take the inverse Fourier transform of this, so what is, for example, let us look at part by part. What is the inverse Fourier transform of this beta tilde? What is it? Does it look familiar? 1 upon 1 plus j omega tau. It is a exponential that is decaying, yeah, right. So, there will be some this constant will carry forward epsilon infinity, right. I have e to the minus t by tau, one more thing will be there, by tau, divided by tau, because it's tau is in the denominator, right. So, this is going to be by tau, and one more critical thing, no, in beta t, I am missing, there is one more term over here, yeah, unit step. Everyone knows what a unit step is, right. So, this is your very simple, right. Without this unit step, if I try to take the Fourier transform of this, this function is only unbounded at the minus time scale, right. So, I need this u of t. So, this is my inverse Fourier transform of beta t. Now, I can get the Fourier transform of epsilon r t. What happens to the first term? it won't be epsilon, just epsilon infinity, there has to be something else. Delta t. Okay. So now that I have got my epsilon r, what is my next sort of objective? Put it into the D equation, right. So our D equation, D of t was epsilon 0, 0 to t, epsilon of t minus tau, and now what do I have to do? I have to substitute this into this equation, right. So before we do this, let's just plan it. Okay. So this, remember, this whole term is called beta t, right. So this whole term is, remember that we cannot actually do any analytical evaluation of this integral. So in FDTD we are discretizing space and time, right. So until the next time instant, until the next time update, what happens to the electric fields or magnetic fields? They remain constant, right. For a given time interval they are constant and then they get updated. That is how FDTD works. There is no analytical evolution. So now this time integral, that this integral in time, what should I how should I go about discretizing it? Right. So I have delta t. So I will split this 0 to t will become a summation over each time instant, right. So I have this, this is my time instant, say this is my time 0 to t. I am going to chop it up into intervals of delta t and then do a summation. That is what will happen. Okay. So my dn, that is my notation for, so all of this is happening at a particular point in space. Yeah. You are asking for this Debye model, is it derived analytically? 0 to t, we are, that's our integral is from 0 to t. This equation? No, because I don't know E, no. If I didn't have E of t in this integral, if I just had epsilon r of tau d tau, which is known as a function of time, then I can perhaps evaluate it, but I don't know. The electric field is sitting in there, which is itself an object of computation. I don't know the electric field. In fact, I am not interested in this D character. I want to remove him and just have equations that update E and H. So this D guy is sort of inconvenient fellow sitting there, because Maxwell's equations is dd by dt, not dE by dt. So I have to go to D and from D come to E. So although D is there, I have to try to work him out of this equation. So dn is the value of displacement field at time instant n. Okay. So what will be the first? So epsilon 0. Okay. Now this first guy in the integral is going to pop out, right. So this whole expression, right, this whole expression over here is going to get substituted into here. So what will the first term give me? Epsilon infinity multiplied by electric field, because electric field is here, at what time instant? T, which is n, right. So this t is the same as n, right. On top I have the continuous time version, bottom is the discrete version, right. So this is the discrete and this is continuous. All right. Next term, here is where the fun starts, right. So I am going to assume that over each time interval electric field does not change, right. So I am going to have a summation. So m is equal to 0 to say n minus 1. Okay. So for example, this is n, right. So I have over this, over this, over this, over this, and finally over this, right. So this is 0, 1, 2, 3 all the way up to this point, which is n minus 1, starting point of the time interval, right. So, I am going to assume the electric field at the start of the delta t remains the same for that delta t, right. So, what will I have over here? I will have E n minus m, okay, and this what will be the summation, what will be the limits of integration? I have introduced the variable m. So, what is the starting point? M delta t to m plus 1 delta t, and what sits inside this integral? Not epsilon r, not it's there, right, staring at you in the yeah, but there is a shorthand notation for that, no, beta t, beta not t but tau. So, let us just check the limits. For example, substitute m is equal to 0, okay. So, m is equal to 0, I will get E n multiplied by the integral from in the first segment, right, from 0 to delta t. Remember, it is a convolution. So, it is E of, supposing I take tau equal to 0, then it is E of t and epsilon r of 0 at 0 time instant, right. So, its electric field is at the future, at the present, and epsilon is at the 0, right. I mean, this is a revision of how you calculate, how you do a convolution, right. So, epsilon r over here of tau is moving from 0 to t. So, this second part over here is moving from 0 to t as m is progressing, and on the other hand, as m is progressing, this electric field value, see, tau keeps increasing. So, E t minus tau keeps decreasing. So, finally, when tau is equal to t, I get E of 0, right. So, if I substitute m is equal to n minus 1, what do I get? E 1, right, at the very beginning. So, it's a, you can choose, you want to have electric field to be constant at the beginning or at the end, does not matter, it's a piecewise constant, right. So, these are the two. So, okay, this is clear. So, if, I mean, this should be really clear, because the rest of it then depends on this part being very clear. What did we do? We just, so we took the Debye model, we took its inverse Fourier transform to find out what it looks like in the time domain, substituted the time domain into the constitutive relation between D and E. That is all that we have done so far. So, what are the approximations? Basically Debye model, and second approximation is this piecewise constant, but that's, there is no choice, we can't do anything better than that, because I know electric field only at discrete time instance, I do not know it everywhere. Why should E be constant from 0 to n? I am calculating E at every time instant of the E cell, right. So, I have a record of E, and this integral needs me to have, I mean, look at the continuous case electric field, continuous case convolution integral. It needs E of t minus tau, and tau is varying from 0 to t. So, it needs E 0 to E t. So, electric field is not constant. Oh, yeah, okay. So, let us just call this tau naught. Okay, yeah, good point. This tau naught is a relaxation time that has nothing to do with this variable of integration over here. Yeah, good point. Okay. So, should we proceed? Okay. So, our next step is, okay, we have got dn. The next step is going to be put it into update equation, right. That is the logical next step. So, what is our Maxwell's equation telling us? So, d dot of n minus half is equal to curl of h n minus half. Okay. I am assuming there is no current, otherwise there will be one more current term over here. So, now this will become dn minus 1 divided by delta t, right. That means, this expression that I derived previously dn not only do I need to take the dn, I have to write down dn minus 1, then subtract the 2. Okay. So, let us write down, let us expand it, the dn term which I had. So, dn, what is dn equal to? Okay. So, notice that this integral appears everywhere. So, we will have a shorthand notation for that also, right. So, I am going to call this just this integral, right. So, this, let us use a different color. This guy over here is what I am going to call beta bar m. Otherwise, I have to keep writing integral everywhere. Okay. Right. So, what is the first term is, I mean, I have my epsilon 0 everywhere, then I have epsilon infinity E n. Now, I see, remember, I want to subtract over here from dn minus 1. Lot of terms may be common between dn and dn minus 1. So, I will just write out the summation and then we will do the subtraction. So, first term over here, so we will start with m is equal to 0. So, it will be E n, right, and then beta bar what? 0, right. I am starting with m equal to 0, right. So, this is going to be, so it is very simple if you just keep track of the indices, E n beta bar 0, right. Next will be E n minus 1 beta bar what? 1, right, and this continues all the way up to E 1 beta bar n minus 1. Okay. How many terms are there? These are how many terms? N terms. Okay. Now, let us write down dn minus 1. This is easy. So, epsilon infinity E n minus 1 first term. Then I will start over here with, will I have this guy? Will I have E n beta bar 0? No, right. So, this term is not there. Will I have the next, what will be the first term of this summation? E n minus 1 beta bar what? See, if there is a n here, there is a n here and there is a n minus 1 here. So, now if I replace this n by n minus 1, this will become dn minus 1 is epsilon 0 epsilon infinity E n minus 1 plus summation m is equal to 0 to n minus 2, right, and then E n minus 1 minus m, right, everywhere. So, the term that will appear over here will be beta bar what? This is the first term of the summation. So, that is m is equal to 0, right. The summation goes on. Finally, what is the last term of this summation? It will still be E 1 beta bar n minus 2. Right. How many terms? N minus 1 terms. Okay. So, now what do we have to do? We have to subtract these two characters and divide by delta t. Okay. So, let us write that over here, dn minus dn minus 1, right, is equal to. So, we should do this subtraction a little bit intelligently, right. So, what would make sense is to keep the, so let's deal with these epsilon infinity terms first and then get to the summation, right. So, there is epsilon infinity E n minus 1, okay, no contest about that. Then there is one term who has no one to be with. So, we will just write him as E n beta bar 0. Okay. Then I have the electric field will be common and the beta bars are different, right. I have E n minus 1, beta bar 1 and then beta bar 0. Now, I am just going to subtract all of these n minus 1 terms from each other, right. That is why I wrote them one above the other. So, these terms I am going to subtract. So, notice what is nice is the E is the same in both these terms. It is E1, E1, En minus 1, En minus 1. So, let us write that as a summation over M. Okay. So, the En minus 1 minus M. Yeah.
In Dn minus 1, the first two terms are for n minus 1 term itself, right?
In Dn minus 1, the first term is
The E infinity, epsilon infinity n minus 1 plus that 0. They come in the first term itself, right?
there is nothing over here, there is no term over here.
That is 0, right?
That is 0.
Yeah, that comes in the first term itself, right? Of the.
Yeah, I mean, I left a blank here because I wanted to align it with the first equation. That's all. So, there is nothing over. So, there is a blank over here. Yeah, okay. So, look at the first term, En minus 1. So, what should M start from? 0. Okay. And what do I have over here? Bracket beta bar M plus 1 minus beta bar M. And the summation M is going to go from 0 to this last term is the hint, N minus 2. Excellent. So, this is not difficult, it is just algebra, keeping track of which term is where and all, right. The only difficulty, actually so far there has not been any difficulty. Once we assume the Debye model is just straight, Fourier transform is simple, then just keeping the terms aligned next to each other are what we have to do. Okay. And then we will substitute this into this term over here. So, we will take a pause over here. Okay. So, steps are clear. Start with Debye model, take the inverse Fourier transform, simplify the convolution, and now I have got a relation purely in terms of E, right. The right hand side is purely in terms of E, and I will equate this to the curl of H term. So, I will get an update relation between E and H, which is what I wanted all along. Okay. Then we will see what happened to that running history. So far, I still need electric field at all past time instants. So, we will deal with whether we still need that or not. Okay.